So with what you know about waves already, we know something about the relationship between the wave speed, the wavelength, and the frequency. So we can look at some fairly just straightforward problems and to see how these work. So the first one is, what's the wavelength of waves? So that would be sort of the distance between the crests. If you splash your hand at a rate of 2 hertz, so 2 hertz is 2 beats per second, so 2 per second, so that's a frequency. And so the wave speed of waves in water in the swimming pool in this setup is 0.8 meters per second, so that is your V. So it's pretty straightforward, just putting in 0.8 meters per second is equal to the wavelength times 2 per second. And so notice the per seconds cancel, and so your wavelength is just 0.4 meters. So that's just sort of a warm-up to get us started thinking about these kinds of things in Chapter 16 on waves. The next problem has a little more information, but it starts to show how sound travels differently in different media. So the speed of sound in air is about 340 meters per second. In water, this is somebody scuba diving and the low frequency, the speed of sound of water is this, okay? And so this question is giving you a lot of extra information, but it's basically saying that if you have a person with ears that are about 18 centimeters apart, right there, 0.18 meters, then one way we locate sounds, especially low frequency sounds, is that we have the sound over on one side and then it travels through the air and it hits our other ear. So we can locate sounds and know which way to turn if we hear a sound. And so this is to look at the difference in speed of sound when we're looking at it in air versus in water. So in air, the speed of sound is 340 meters a second, and it's asking us to calculate the time between signals if we have the signal, the alarm or whatever, at one ear, and then that's got to travel through the air to the other ear. And so that time for this signal, that's the question. How long does it take? So if we're going 340 meters a second and we're looking at a distance of 0.18 meters, there's no acceleration here. So this is fairly straightforward. We say speed is delta x over delta t. This should feel like day one again. And we're asked for the delta t of the signal, the time between the sound being in one ear and then getting to another. So this delta t, the time that we experience, is just going to be delta x over v, or 18 meters, the difference between our two ears, right? And then the speed of sound, 340 meters per second, or that gives us a time difference of about 0.0005 seconds, which is about 0.5 milliseconds. Now, it turns out that we're reasonably good at differentiating sounds that come at that speed. This is what this first thing says. It says, if the delta t, that we're pretty good at telling the difference between things that are on this scale. But if it's going to be faster than that, then we won't be able to tell which ear things came from. So that's what's going on in air. In water, the speed of sound in water is much faster. So delta t of the signal, we would expect would be faster, right? We use the same delta x over v, or 0.18 meters over 1,500 meters a second. That's about it's about 5 times as fast, thereabouts. So this is going to be about 5 times. So I get 0.12 milliseconds. And so this is really below the threshold that the problem gave us that your ear can actually differentiate. So when you're underwater, it's hard to use this trick to differentiate between where a sound is coming from compared to in air. Now, we don't just use this to locate sounds, but this is one way we do it. And so this tells us that this works fine in air, which makes sense. That's where we live. It doesn't work as well underwater.